So our first talk of the day, we're delighted to have Simone back to talk more on Wilson loops and AdS.
Okay, thank you very much. So after yesterday's introduction, today I will talk about some more recent work that I've based mainly on this series of papers with various people, Raghu Roivan, Kali, Saidi Komatsu, and Korea. So I'll go quick over this because we already discussed yesterday. So in any for superior mills, it's a very natural operator to consider, which is a generalization of the usual Wilson loop. It's this operator where in the path ordered exponent we have both the usual Wilson loop type factor and the coupling to the scalar field. So it's parameterized by a choice of a loop in space-time and the choice of function theta, which parameterizes this coupling to the scalar fields of the theory. So this is the general operator. Then special choices of what curve you take and what scalar coupling you take can lead to operators which preserve some supersymmetry. And so there are two large families of operators that I didn't discuss yesterday. So I'm just here reminding what they are, but I'm not going to use them a lot. So there is one family constructed by Zarembo in 2002. So here you just take an arbitrary curve on R4, and then there is a simple way to choose the scalar coupling so that the operators only couple to 4 scalars, and the Wilson loop is supersymmetric. It preserves up to 1/16 of the supersymmetries, and all these operators have trivial expectation model. There is another large family which I constructed with Dav Drucker, Rich, and Trancanelli in 2007. So these are defined for arbitrary curves on a tree-sphere. So you pick a tree-sphere inside your space-time, you put any curve there, and then there is a precise way to choose this coupling in a way correlated with the shape of the loop that you take, so that the operator preserves, again, up to 1/16 for the supersymmetry. These have, in general, non-trivial expectation model. There is an interesting subfamily of these, which I will need later, so I will come back to this, for loops defined on a 2-sphere. So I will come back to this kind of operators later.
Sorry, in order to be able to find the answer by localization, how much supersymmetries do you need?
So up to, well, the examples that we know are no less than 1/8. So for the more general 1/16 case, there is no localization, at least not yet. Okay. So the most supersymmetric cases that I was discussing yesterday are the Half-BPS Wilson loops. So we can either take a static quark corresponding to an infinite straight line contour and couple to a single scalar, so an operator like this. I will take the scalar to be phi6, just as a choice of conventions. And as I discussed yesterday, this preserves 8 Poincare supercharges and 8 superconformal supercharges. And similarly, there is a very closely related operator, which is the circular one, which can be obtained from this one by a conformal transformation, and that also is Half-BPS. It preserves linear combinations of Q and S, and it has a non-trivial expectation value we discussed yesterday, given by the matrix now. Okay, so today the type of operators that I'm going to be discussing are these correlation functions. So I will use this notation, this double bracket notation, correlators of several operators inserting their components along the loop. So given any choice of operator so in the adjoint, so just take some adjoint operator and consider this object, you sprinkle these adjoint operators inside the ordered trace. So this notation just means that you have these Wilson line exponential factors, and then at various mark points along the loop you insert some adjoint operators, and then you take trace path ordered, so the whole operator is gauge invariant. Okay, it depends on the position of these points, okay? And then we normalize by the expectation value of the Wilson loop, so that, for example, insertions of 1 just gives 1. So this normalization will be trivial in the case of straight line, but it's not trivial in the case of the circle, we discussed yesterday. for most of the talk, so for the first part of the talk, I will focus on the straight lines because it's a little bit easier to do calculations, but one can always go from one to the other by conformal transformations. And provided you normalize by the expectation value, these correlation functions map nicely from line to circle. Okay. So to understand the structure of this object, well, let me first say what is the motivation to study these things. Well, one motivation which was pointed out by Zucker and Kawamoto a while ago is that this kind of object arises naturally if you consider deformations of the Wilson loop. If you start with a Wilson loop and say the Half-BPS one, and you consider a small deformation of the contour, then that can be described by, for a small deformation, by bringing down some factor of field strength, especially if you're just forming shape, which is an object of this kind. And then you will have an integral over the insertion point. But so as a motivation, this kind of correlators are a building block to understand deformations of Wilson loops. So knowing these correlation functions for arbitrary operators, in principle, tells you how to compute expectation value of general Wilson loop, of general shape. So you start with Half-BPS one as a simple starting point, you deform it, so then you learn all the correlation functions on that. If you know all the correlation functions, you in principle can reconstruct Wilson loops of arbitrary shape. That was a motivation to do it. Okay, so to understand a little bit better the structure of this, we can, so I already anticipated this in yesterday's lecture, but let me go over this again, so we can understand what is the symmetry of, of the problem. So what are the symmetries preserved by these Half-BPS operators? So there is an SO3 for rotations in the directions of problem in the line. There is an SO5 rotating the 5 scalars that don't couple to the Wilson loop. And there is a SL2R one-dimensional conformal symmetry, which is translations, dilatations, and special conformal transformations along the direction of the line. And this, together with the supercharges, form the supergroup as before, which is a one-dimensional superconformal group. So as I was saying yesterday, this means that these Half-BPS operators can be viewed as one-dimensional conformal defects of the theory because they preserve a one-dimensional conformal subgroup. And this then implies that operator insertions, so operator insertions inside the Wilson loop will be labeled by representations of the symmetry group. In other words, as usual, these operators will behave as operators in a one-dimensional conformal system. They will be characterized by their SO3 cross SO5 representations and by a scaling dimension of SL2R. They can be organized in primaries and descendants. So they have all the structures that we expect in a conformal theory, and now just living in one dimension on this Wilson line. Okay, so for example, two-point functions, as usual, will be fixed by the scaling dimension of the operators. Three-point function will be completely fixed up to a constant. Now here I'm dropping this double bracket notation, and occasionally I will do that. But when I talk about this, you should always keep in mind that what I'm really discussing at the basic level are these operators. But once you realize that they behave like correlators in a one-dimensional system, I will sometimes be a little bit cavalier and drop this double bracket and maybe just use the bracket. But they always mean, at the end of the day, I mean this system of insertion inside the Wilson line. But they behave just like a system of one-dimensional correlation in a circuit.
Question.
Yeah.
So does this three-point function have something to do with the three-point function you would compute just in 4 dimensions?
In principle, no. So this is a different sector of the. So what, you mean like three-point function of single trace operators?
Well, yeah, the 3 are also operators of n equals 4 super n mills.
Right, but so there is an important difference. So these are inserted inside the trace, right? So, for example, I'm allowed to talk about I'm allowed to talk about insertions of, say, just phi.
Right.
Well, I'm not allowed to talk about trace phi as an operator, for example. Right? So it's a different sector. This is like the open string sector of correlation functions versus the closed string sector. Okay.
Just to make sure, sorry. So if you take a straight Wilson line and you want to deform it in some direction,
yes,
right? you replace that by a straight one with some insertion.
Yes, that's the
Okay, that's the idea. So you have to decide which insertions correspond to a very
Right. So if you just do that deformation in some transverse direction, what you insert is literally just the field strength of what is in the exponent of the width.
But that's kind of the infinitesimal.
Yeah.
Okay, and then you will be able to integrate that. Okay.
Yes, that's in principle the idea. Yes. In practice, I'm not going to do that. That's just a motivation for why we look at this. But in the end, I'm more interested in this as a system, as a one-dimensional conformal system of correlation functions, and try to use conformal field theory techniques to understand it. Okay, so 4-point functions are more interesting, as Fernando was discussing in the lecture. So in one dimensions, they're a little bit simpler than the general case. So say for the 4-point function of 4 identical operators, they are fixed up to a function of a single variable in this case. So in Fernando's lectures, he had 2 cross ratios, U and V. In one dimensions, those 2 are not independent. There is just one single real cross ratio, which is denoted here by chi. This conformal invariant cross ratio. The fact that it's 1, it's easy to understand, because if you have a conformal symmetry and you have 4 points on a line, you can fix 3 points, and then you'll have the position of the 4th point as your free parameter, which is this chi. Okay? And then, as usual, we expect that this function will have an expansion in terms of conformal blocks. Again, things are a little bit simpler here than the general case. The conformal blocks in one dimensions are completely known. They're just given by this geometric 2f1 functions. So here, h is the dimension of the intermediate operator, which appears in this expansion. These are just the OP coefficients, which are basically the square of the 3-point function coefficients. So it's, I don't have, luckily, to go through this in very much detail, because Fernando explained this in the more general case. In one dimension, it's just a little simpler, in the sense that there is just one cross ratio, and the blocks are simple. Okay? So, as I said, so my motivation, besides the deformation of Wilson loop, is just that this may be an interesting toy model of a one-dimensional conformal system, where maybe we can do many calculations exactly. It has a lot of symmetries. There is some sectors of it which are captured by localization, so maybe putting everything together, this could be an example where we could fully solve some kind of conformal system, in this case in one dimension. And maybe also bootstrap techniques can be applied to this system, either numerical or analytical, and there is some recent work by various people that have started doing this. Okay, so let me now discuss some particular class of insertions which are especially simple. So there is a multiplet of insertions which are I would call elementary insertions, because they are the simplest and nicest kind of operators that you can consider. So this is sometimes called the super displacement multiplet. It's a multiplet of 8 bosonic plus 8 fermionic insertions. So what are they? So the bosonic ones are the insertions of the 5 scalars that don't couple to the Wilson loop. Again, to avoid confusion, these scalars are in the adjoint, so by themselves they are not gauge invariant operators. But here I'm discussing insertions of these things inside the Wilson loop, so I can talk about insertions of this operator. And as an insertion in this one-dimensional system, this is an operator which has scaling dimension 1, and it's protected. And it transforms in the 5 of SO5, represented by the Wilson. Okay? And then there is, in the same multiplet, there is a displacement operator, which is literally what you get if you do deformations in the directions orthogonal to the line. And because the exponent involves a plus phi 6, what you actually get is not just the field strength, but the field strength plus the derivative of phi 6. So this is called the displacement operator. It's a basic operator that you have for any conformal defect. It just describes the deformation orthogonal to the defect. In this particular system, it happens to be in the same super multiplet of this simpler operator, which is the scalar, which is the super conformal primary of this multiplet. And then there are 8 fermions, which are not right here. So these all absolutely protected scaling dimension. The fact that the displacement operator has dimension 2, that's actually a general fact for any defects. It doesn't depend on supersymmetry, it just follows from conformal symmetry. So that's always true. What is different in this case is that it belongs to this super multiplet. So there is a superconformal primary of dimension 1, and the displacement is superconformal descendants of that. Okay, but this is a very general fact about defects in general. Okay, so 2-point functions of these basic insertions are simple. So this dimension 2 is protected, so it's just given by this, and it's just specified by this function of coupling. And the same for the displacement. The two functions are related because they're in the same multiplet. And these functions are given, they are both proportional to what is called the Graham-Straubing function, introduced a while ago by Correa, Mandelstam, and Sever. So this is a function of lambda, or in general, lambda and n. Here I'm writing the results in the planar limit because I will do mostly planar, but in principle we can also write it for finite n. And these functions can be obtained by localization. I will discuss this a little bit later, but they are given explicitly in terms of these functions.
So is there any reason why these functions cannot be removed by a normalization of the insert?
So these operators are protected, so the normalization makes sense in principle, provided there is a natural one. And because the displacement operator is related to deformations, there is a natural relation to it, to the stress tensor of the stress energy tensor. So there is a canonical normalization for it. So it makes sense to talk about this. So this is sort of analogous to, say, CT in usual CFT. Here you can define a C for the displacement operator, which has a meaningful normalization. So,
And for the scalars?
well, these are because they are in the same multiplet. So
I mean
yeah, they're in the same supermultiplet. So
Oh,
once the displacement has some normalization, the one for the scalars. Okay. 3-point functions of these are trivial because of the representation here. There is no 3-point functions between these insertions. You cannot write down a 3-point function of, say, 3 phis or 3 AdS, so because of the SO5 process or 3 structure. So the next thing you can study about this kind of simple insertions are the 4-point functions. So the 4-point functions, as I said before, they are more non-trivial because they encode information about the operator spectrum and the OP, that is the OP expansion. So our motivation in the first paper where we looked at this was to compute these 4-point functions, and we did this as strong coupling using the string theory. So there are also results known up to 1 loop order just in perturbation theory, usually on this. The most recent paper on this is a paper by Kiryu and Komatsu, where they computed the 4-point functions of these operators explicitly by doing 1-loop calculations. What we did is calculation of the string theory, so as I will review, it basically boils down to a weak invariant calculation in AdS2, where AdS2 is the Worldsheet, is the string Worldsheet dual to these operators. Okay. So this again we reviewed yesterday. So Wilson loops are dual to minimal surfaces ending on the contour of the boundary. Okay, so this is a picture. Now, more precisely, the full complete dictionary relates the Wilson loop expectation value to the string partition function. So it's the path integral of the string sigma model with boundary conditions on the fields. So X capital M here denotes the Worldsheet coordinates, say the 10 coordinates. And we do the path integral over the coordinates and the fermions with the Dirichlet boundary conditions that this end on the curve that is on the space-time and on the sphere it describes the scalar coupling. So this is the general description. At large lambda, this reduces to e to the minus regularized area, but this in principle tells you how to go beyond that by just doing perturbation theory with the sigma model. Okay, so I will not need the fermionic part of the action, just the bosonic one, and it will be convenient to use the Nambu-Goto form of the action, which I write here. And we'll use this explicit coordinate system where so this is just AdS5 in Poincare coordinates here, and this is a particular coordinate system on the 5 sphere. So Y are 5 Cartesian coordinates. They are unconstrained, they are not angles. So this is like a conformally flat form of the metric for the 5 sphere. Okay. So in these coordinates, what is the string Worldsheet dual, say, to the infinite straight line? That's easy to see. that it's just a straight string going down all the way from the boundary to z equal infinity, just a straight string. So it has the topology of a half plane. Explicitly, it's just given by, so I will denote S and T, by S and T the Worldsheet coordinates. T goes from minus infinity plus infinity, and S from 0 to infinity. Okay, so the topology of the Worldsheet is an half plane, and the explicit embedding that gives this Worldsheet is just the z, the Poincare coordinates equal to S, x0 equal T, and all other coordinates 0. So y equals 0, it means picking a point on the sphere, say the North Pole. So that corresponds to picking one of the scalars. So this is the Worldsheet dual to the straight line. And so I didn't say this yesterday, I went straight to the circle, but I could have done the line first. It's, again, the Worldsheet will be an AdS2. It's an AdS2 in Poincare coordinates. So the Worldsheet is an half plane. And if you do the induced metric, it's just this. It's AdS2 in Poincare coordinates, where S goes from 0 to infinity. The boundary is this infinite line. And then you can go to the circle if you want by doing conformal transformation, and you get instead the Poincare disk, which is this, where the boundary is the circle. Sigma goes from, again, 0 to infinity. Okay. So you can do calculations with either model. I will focus on this one because it's technically slightly simpler, but you can go from one to the other by conformal transformations. All right, so I don't have to go through this in detail. So you realize that that's the minimal surface dual to it. It preserves the same symmetry as the operator. So the AdS2 realizes the conformal, the one-dimensional conformal symmetry, you said 2R. And then there are, of course, the SO3 cross SO5. So the SO5 is the rotation in the directions of the 5 sphere once you pick a point. So you pick a particular point, and then you have left over SO5. And there is an SO3, which in these coordinates is the rotation of the 3 transverse coordinate in the 4 Cartesian R4. We pick one, which is the line, and then you have the remaining 3. So it's literally the same symmetries that you had on the gauge theory, just realized explicitly in these coordinates. Okay, so you have an SO5 rotating the y's, and you have an SO3 rotating the x. Okay, so then you can expand the sigma model around this surface, and that will tell you what is the dynamics of the fluctuations of this surface. So you can read off the interaction between these fluctuation fields. To do this expansion, it's convenient to use static gauge. So stay with Nambu-Goto and use a static gauge. So static gauge means that we identify the Worldsheet coordinates with 2 of the space-time coordinates. So in this case, T is identified with x0 and S is identified with Z. Those will not fluctuate. And then you just have the physical 8 transverse bosonic fluctuations plus the fermionic ones, which I will not discuss here. So you pick this gauge and expand your Nambu-Goto action in terms of fluctuations. You get some Lagrangian with interactions. So you have a quadratic term in the fluctuations, a quartic term, and so on. And because you're expanding around this minimal surface, in practice what you get is just some particular field theoretical model of fields propagating in AdS2. So it comes from expanding the string action, but once you reach this point, you can view this as an AdS2 theory with a collection of 8 fields propagating on this AdS2 background, and they have some interactions which are AdS2 covariant. So G here is the metric of AdS2. X and Y are these fluctuations. Okay? So you can first read off the spectrum. So what is the spectrum? By just looking at this quadratic part. So the quadratic part tells you the masses of these fields. So you have the 5 scalars are massless on the S5, and then there are the 3 scalars inside AdS, which have mass square equal 2. And then you can just follow the usual thing that you do in AdS CFT. You have some fields in AdS2, they have this mass. So you solve the wave equation, it tells you what are the scaling dimensions of the operators at the boundary. Now the relation is delta minus 1 equal m squared, because we are in D equal 1. So for m squared equals 0, the massless fields, you get delta equal 1. So that's what you expect. This fluctuations on the 5 scale direction are dual to the insertion of the scalars, which are protected at dimension 1. And for m squared equal 2, you get delta equal to 2 minus 2. So that's the insertion of this displacement operator. And so the fluctuations along S5 are dual to the scalar insertions, and the fluctuations in AdS are dual to the displacement operator insertion. And so once you understand the dictionary, you can go ahead and just compute the 4-point functions by usual AdS CFT techniques. Now you just have an effective model in AdS2, which came from the string theory, but I can just give it as a model in AdS2 and compute 4-point functions. So this is the picture basically of what calculation is doing. So this is say the line where you have the Wilson line operator. This half plane here, the string Worldsheet, which is dual to it, is an AdS2. You insert some operators on this line, and then the 4-point function at strong coupling will be computed by this AdS2 Witten diagram, in which you have the interaction of the dual fluctuations at some point on the Worldsheet, and integrate over that point. So it's literally just a Witten diagram. Okay. So before going on, it's worth to make some comments. So these calculations, as I described them, are very similar to what we usually do in AdS CFT. They are similar to the usual Witten diagram calculation that you do in supergravity. But it's a quite different interpretation. So when we do supergravity calculation, what we are computing is 4-point function of single trace, or 3 or 4-point function of single trace operators, like trace z to j, which are dual to closed string states. So we use the supergravity to do the calculation. We are computing single trace operator correlation functions, and the coupling function in that case is 1 over n squared, which is what comes from the supergravity action. Now here, in our case, what we are computing a correlation function of insertions inside the Wilson loop. So actually we are computing the expectation value of a single trace operator with stuff inserted inside. And so these are dual to open string fluctuations. They are not closed string states, of course. And the expansion parameter here is not n. It's not 1 over n squared. N has been taken to infinity. We are in the planar limit. The expansion parameter is 1 over square root lambda, because we built these Witten diagrams using the Worldsheet action. Okay, so technically similar to Witten diagram calculations, but it's a different expansion parameter and a very different kind of states. It's not local single trace operators, but it's insertions inside the Wilson line. Okay. So some other comments. So in this, because we expect the string theory to be UV finite, all the calculations that we could do with this model should not have any divergence. So this is kind of a model where we could, in principle, compute loop corrections to Witten diagrams and expect that everything goes fine, no divergences. So it is one motivation to look at it is that it's an interesting toy model to learn more how to do loops in AdS, because AdS2 is a little bit simpler, and also we don't expect divergence here. Everything should be finite, and in many cases we are controlled from localization, so we know what to expect. So for example, we want to compute loop corrections with 2-point functions, so more interesting in loop corrections with 4-point functions. Okay. Okay, let me go briefly over this. Let me also say that what I'm discussing here are just correlation functions of operator insertions on the Wilson line. Now, when you have a defect in a conformal field theory, there is more data that you could study, because you can also consider correlation functions of the defect with possibly insertions on it, and other operators, conformal operators of the theory away from the defect. So this is what is called in the defect literature the bulk defect OPE data. So here bulk just means away from the defect, it doesn't mean AdS. So a bulk defect correlator would be a correlator where you have some single trace operator away from the defect, and then you have the defect and some operators from the defect. So those kind of observables are other kind of natural observables that you can compute in defect conformal field theory, and they correspond to, in the AdS picture, they would correspond to things like this. So you have say, an insertion of a single trace operator somewhere away from the defect. Here you have the defect with one or more insertions. And then on the string theory side, there would be some kind of mixed open-closed amplitude where you have your open string, you have some closed string vertex operator on it, which couples to this supergravity mode, or in general closed string mode, which describes the single trace operator. And then this amplitude will describe this bulk defect data. Now, one can do this. I'm not going to discuss it in this talk. These processes are suppressed by powers of 1 over n. So if we literally are in the n infinity limit, we can just focus on the correlation function of defect operators. And here I'll just focus on those. So one can study this as well. I did this in a recent paper with comments. Okay. So the calculation of this is pretty standard. I'm not going through the details. It's just literally you take 4 boundary propagators using the interactions of this theory and integrate it with a point. This is the result that you get for this diagram. I just want to give you a feeling of what it looks like. So to write it in a compact form, it's useful to introduce some auxiliary vectors, YA, and multiply those by this coordinate so that you soak up the SO5 indices and you have an object which has no indices. It's just a useful bookkeeping parameter to write down the correlation function. And then it takes this form where chi is the conformal cross ratio, and psi and zeta are just the cross ratios in these auxiliary SO5 polarization space. And GS, GT, and GA are functions of cross ratio in the 3 channels corresponding to singlet, symmetric, and anti-symmetric representations of the SO5. Okay, so they are given explicitly here. Explicit form doesn't matter too much. Just to show you that you do this calculation, you get something pretty explicit in terms of logs and rational functions. So the D functions that you get from this kind of calculations for people who have done this usually involved in higher dimensions, something like dilogarithms and things like that. In one dimension, for the specific values of scaling dimension that we have in this problem, they become elementary, all these logs. Okay. Once you have this, you can write the expansion of this in blocks and read off the OP data. I'm not going to do that in detail. Just a couple of comments. So there is one consistency check that you can do if you look at this GT, which is a symmetric traceless channel. So first of all, what do you do when you have this expansion? Well, what you want to read off are the scaling dimensions of the intermediate operators. And in perturbation theory, when you have logs, it means that you have some anomalous dimensions of operators that appear in the OP. That's basically because in the OP expansion you have chi to the h, where h is the scaling dimension. If h has an expansion in powers of 1 over root lambda, perturbatively that generates log chi. If you expand in chi, h0 plus 1 over root lambda and so on. So log chi's are related to anomalous dimensions. And in this expression you can check, for example, that if you look at dimension 2 in the symmetric traceless channel, there are no anomalous dimensions. That is corresponds to the fact that there is a protected operator, which is a symmetric traceless product of 2 scalars. So that's analog to the chiral primaries that we have in the usual closed string sector. There you have symmetric traceless representation of SO6. Here you have symmetric traceless representations of SO5. So these are protected operators, and they have protected dimension. So in general, you have those that you can have rank J symmetric traceless, and they're protected. More interesting, you get non-protected operator in the singlet channel. So that the first operator that appears there is just the singlet product of 2 y's. So just so that we don't lose track of what we're doing. So here I'm describing the 4-point functions of the y's. So the OP channel will include all the operators which are built out of products of these y's. So in general, y derivative is y. The lowest line one would be just y singlet ya, ya. And if you look at the structure of the logs here, you can read off that this operator, ya, ya, has this expansion as dimension 2, plus a correction which is negative, minus 5 over root lambda. So 2 is just because y is dimension 1, so if you put them together, leading order is 2, but then there are corrections due to the interaction, so it's 2 minus 5 lambda. So what is this operator? So this is the lowest lying singlet operator from coupling. So if there is no level crossing, as we go from strong to weak coupling, we would expect that this should match up to the lowest lying singlet at weak coupling. The lowest lying singlet at weak coupling is just the insertion of phi 6, which is the SO5 singlet, which couples with the Wilson loop. It's the one that appears in the Wilson loop trace. The dimension of that operator was computed long ago by Fernando and Juan, actually, just by doing perturbation theory at weak coupling. The dimension of that is at weak coupling 1 plus corrections, lambda over 4 pi squared. And what seems natural to propose is that this operator matches smoothly to the lowest lying singlet at strong coupling, which is now this singlet two-particle state, which is a bound state of 2 y's. So this YA state should match up onto this phi 6 insertion. Okay, and well, this idea is supported by the structure of this expansion because it's 1 plus order lambda at weak coupling and 2 minus 1 over lambda strong coupling. So there should be an interpolating function of lambda which describes the dimension of this unprotected insertion on the Wilson line going from 1 to 2. Okay? So I don't know what this function is. I just plot a random function here which goes from 1 to 2. But there should be a function that goes like this. Okay? So in some sense, this is like the singlest unprotected state in this closed string, in this open string set. So it's kind of analog to Konishi, but it's very different from Konishi because Konishi has a very large dimension, strong coupling. This one just goes to 2 plus minus 1 correction.
Are there any counterexamples to this assumption of no level crossing in any other sectors, or is it always a safe assumption?
Yeah, not that I don't know any counterexample.
For n equals 4, I mean, is it always?
Yeah, I mean we don't, unless there is some special reason to set some degeneracies or something.
No, you have integrability. You have integrability. You have level crossings.
You don't have.
No, you can.
You do.
can.
With
That's the
integrability,
point.
you can have level crossing because n is equal to infinity. So for any finite n, you cannot.
You cannot.
But in the you can.
Yeah.
Okay, so in the planar limit you can.
In principle.
Yeah, usually level crossings imply an extra symmetry floating around.
Okay. So in the solutions of the Y system for n lambdas there are level crossings?
Yes.
There are, okay.
Yeah, so
I know we
Konishi
have
crosses
some,
everyone. So it goes from 2 to infinity and it crosses all the protected operators of
Okay.
dimension 4, 6, 8.
But in this setup it's a safe assumption, I guess, because...
No, but in a second. Yeah, okay.
Yeah, so Konishi is an operator with that starts at dimension 2, it has a spin 0, and the dimension grows up to infinity, but you have also the double trace operators, etc., protected, and these are dimension.
But they all go
But
level
they're not
lambda, so they all go to...
No, they don't.
Okay.
I mean, they are protected operators of dimension 4.
Oh, the protected, yeah,
and,
yeah.
yeah, there are some in this
Yeah, yeah.
in the singlet representation. But the question I had is related to this, but it's the following. So that's a clever polygon. They have some argument to say that single trace operators should be dual to string states, and that's the reason why they acquire a large
Yes.
dimension.
Yes.
Can you try to think
Yeah,
about
here.
the opposite of that here?
Yeah, here there doesn't seem to be such an argument because at strong coupling, all you can do is add oscillators to this very long string, and that will always give dimensions which are multiples of integers plus small corrections to interactions. So if you want a large dimension, you have to put a lot of oscillators on this string. So if you just have a few, you add 2 oscillators in these y directions, it looks like you can only produce something like this, dimension close to 2. All right. So maybe there will be some integrability-based or bootstrap-based approach where we can have more information about this interpolation, whether this idea is correct. More generally, one can ask whether there is some way in which integrability is manifested in these AdS2 calculations that I'm describing. So I'm just computing some kind of AdS2 S matrix for these fluctuations. It's a natural question to ask whether there is some sign of integrability in this width and amplitudes. So this should come from the underlying integrable string theory, and maybe there is some analog of S matrix factorization at the level of this AdS2 width entitlement. Kind of open question which may be interesting to analyze. So how much time do I have? Okay. So now let me switch gears a little bit and discuss how to obtain some exact results in this system by localization. So to get exact results, we have to map line to circle because all the exact results are more naturally written in terms of the circular geometry. But it's not difficult to do that mapping. So at the level of correlators, provided we normalize by the expectation value of the Wilson loop, we basically just have a conformal transformation between line to circle. And so, for example, a two-point function will go from this form on the line to this form on the circle. All these distances become distances on the circle. And the four-point function will be similar, where the cross ratio now becomes the cross ratio on the circle, which is the ratios of the signs. But the functions itself don't change. Just because you can use conformal transformation to go from one to the other, you only map the coordinates. You don't get new functions. So I'm just saying that all the correlation functions that you computed on the line, you can just rewrite them on the circle with the same function. Okay? We have to divide in this case by normalization, the function value. Now to use localization to get information about the correlation functions, we have to embed this circular Wilson loop into this larger family of 1/8 operators, which are Wilson loops defined on a two-sphere. So before I was talking about Wilson loop on a three-sphere. There is a subclass of those which are a little bit more supersymmetric, in which you pick a two-sphere instead of a three-sphere, so you restrict the loops to 2 dimensions. They couple to 3 of the scalars. Let me just tell you what the explicit form of the operators is. So this is the operator that we constructed. You just pick some two-sphere in space-time, say explicitly it's convenient to give that in Cartesian coordinates, and the radius doesn't matter, so I'm setting it to 1. Pick that sphere and put a contour on that sphere, any contour, and then the scalar couplings will be given by this form. It's not obvious that this is the form of theta, where theta is a unit vector, but it's true, it's not check. Okay, so this operator preserves 1/8 of the supersymmetry, and the circular Half-BPS Wilson loop is just a special case of this construction. You just take a large circle of ES2, an equator. If you take an equator, this thing here collapses to just a constant, and it couples to a single scalar. In general, it couples to 3 scalars. Okay? So these operators are captured by localization. So there is a variant of Peston's original calculation in which you can apply to this more general 1/8 operators. And what do you get is that the path integral localizes not to a matrix model directly, but to a 2-dimensional theory. So if you do localization for these operators, you get localization to 2-dimensional Giombi's theory. Okay, so more precisely is a truncation of 2-dimensional Giombi's theory to the 0 instanton sectors. You drop all the instantons and just compute things in that 2-dimensional theory. And these Wilson loops are just mapped to the usual Wilson loops of 2-dimensional Giombi's theory. Because 2-dimensional Giombi's theory is invariant under area-preserving diffeomorphism, this means that the expectation values of the Wilson loops are very simple. They just depend on the area of these contours and not on the shape. So what you find is that for all these 1/8 operators, for any contour, the expectation value is given again by these Bessel functions. You just have a rescaling of the tooth coupling by a factor of the area. So if A is the area of the Wilson loop, you get this Bessel function, where lambda prime is just this rescaling. And the expression, the well-known expression for the Half-BPS one is just when you take the equator. So A is equal to half of the area. And there is also, so the interesting thing is that you can do localization for a large class of operators defined in this sphere. You can put any number of Wilson loops, and you can also insert several local operators away from the Wilson loops or inside the Wilson loops. And this combined system preserves the same supercharges. It shares supercharges. You can apply localization to all of these operators together. And what localization tells you is that this correlation function, this general correlation function in the four-dimensional theory, maps to this one-dimensional theory where the Wilson loops goes to the usual Wilson loops. And the scalar operators map to insertions of the field strength of two-dimensional fields. What are these operators? Well, these are just some special kind of chiral primaries. They're just chiral primaries of this form where the direction in the R-symmetry space is correlated with where you insert. So this is a typical constructions of operators that present some supersymmetry in this localization context. So in this particular example, you take this operator like this. So this is just an operator of the form y of phi to the j, because x squared is 1. So you can think of this just as a usual chiral primary in which you have some null. So it's literally just like z to the j, phi 1 plus I phi 2. More generally, you could write that as choosing some null vector and write it as epsilon dot phi to the j, where epsilon is null. So here you just take a particular null vector which depends on the position where you put the operator. That null vector is just given by x1, x2, x3, and I. It's null because we are putting this on a sphere. So if you do this, this operator preserves the same supersymmetry as the Wilson loop. And these operators actually were introduced before independently by Drucker and Plefka. We just studied these operators by themselves and realized that they have nice properties, like their correlation functions are position independent due to the fact that you choose them in this particular way. Okay? So now in this system, they work well together with the Wilson loops, and they map to insertions of the two-dimensional field strength of the elements. And again, their correlation functions are completely position independent. Any questions about this? All right, so now we can also insert this kind of operators inside the Wilson loop, and so we will have a sector of insertions which are completely captured by localization. And the type of operators that we can insert are just these ones that I described. Now, when you put them inside the Wilson loop, it just means that you have to correlate the combination of scalars that you put with the position on this circular Wilson loop. It's just the explicit form. And then you can consider correlation functions of arbitrarily many of these operators on the circular Wilson loop. And this will be a topological subsector of the defect CFT in the sense that these are completely position-independent correlation functions. Okay? But from this, you can reconstruct the general 2-point and 3-point functions of the physical operators, because those are completely fixed by conformal symmetry. So you can use localization to compute things in this topological subsector, but that's enough to reconstruct the structure constants for general chiral primary insertions inside the Wilson loop. So this is the form that is fixed by conformal symmetry. So if you choose these y's to be the ones that are given by that construction, all this collapses to a constant. But because this is completely fixed, you can reconstruct this general structure constant from that calculation. Okay, so this, maybe I need to speed up a bit. So how do you actually do this calculation by localization? Well, the idea is that since these insertions are related to EML's field strength, and you know that insertions of field strengths are related to the formation of Wilson loops, you can basically relate these insertions to derivatives of the Wilson loop expectational value with respect to area. Now, once you are into DMLs, there is area preserved in diffeomorphism, so all you can do is just derive with respect to area. It doesn't actually depend on the precise shape of the formation. So to reproduce correlation functions of insertions of these guys, you just take derivatives with respect to area. If you want L of them, you do it L times. So this will insert this inside, but just a 1 power. So for example, this is a very simple way to obtain the Stralin function that I'll Sena, Severa, and Correa years ago. You just take the log of the Wilson loop expectation value with respect to area and take area derivative twice. That gives you this I2 over I1 function. Okay. And you can, for example, with the 4-point function, you get this function of coupling, which is an exact result. And then you can compare with our Wilton diagram calculation we had before. So that was a complicated expression in terms of cross ratios and all of that. You take that expression, specialize it to this particular operators. So that expression is general, works for any phi. You specialize to this phi twiddle, which are the ones captured by localization. Remarkably, that complicated expression I showed you before with the chi's and so on becomes a constant once you specialize to this. And if you expand it, if you expand this at large lambda, it matches what we had in that calculation. Okay. So let me describe this as left-hand insert. Okay. So it's easy by taking the direct derivatives to describe insertions of single powers of this one. Once you take a derivative, you insert one of this. But you can ask how to construct the more general operators, which are phi to some power. Okay. So to do that, you use the same idea, and then you use OPE logic. So you want to understand how to define, say, the square of the operator phi square. By phi square, I mean a normal ordered operator which has some 0 1-point function, say, and is orthogonal to other operators. So how do you do that? Well, you realize that this correlation function is position independent, so you can move around these phi's freely. But once you bring two phi's together, the OPE tells you that that product should be possible to be written in terms of actual normal ordered operators. So the product of two phi's will be the phi square operator that we want, possibly phi and the identity. So OPE tells you that the OPE is closed in this topological subsector. It just tells you that you can write this. So you can reconstruct what this operator is by just imposing this OPE and subtracting these terms. Okay, now practice this, and then you take the correlation function on both sides by inserting another phi to fix this constant. Okay. Now the details of the constructions are not terribly important, but the idea is basically this. So at the end of the day, to do it in practice, you realize that this is just a process of orthogonalization of a set of vectors. What we are doing is just constructing this new basis of normal ordered products, which are orthogonal. They are linear combination of products of single letter insertions, and they start as this plus other operators. So this problem can be solved by just the Gram-Schmidt procedure. You start with a set of vectors which are not orthogonal, and you build a set of new vectors which are orthogonal. So the procedure is straightforward, but the expressions become slightly complicated at the end. But here is the final formula, just to tell you that there is a very explicit construction. If you want to know what is the power, the phi to the L, the chiral primary of the length L, it's a linear combination of products of phi's with coefficients given by derivatives of the Wilson loop expectation value. So this is the determinant. So there is a complicated determinant structure which tells you what are these operators, and then you can use this to reconstruct the arbitrary correlation functions of these operators. So you get a very large set of exact results for a subsector of correlation functions in this one-dimensional CFT on the lambda or on the same. So here, just flash some explicit examples of 2-point functions. So you always get this Bessel functions because they all come from the basic Wilson loop expectation value, and all you're doing is taking complicated derivatives of that and taking determinants. So you get some fully explicit but combinations of the Bessel functions. These are the 3-point functions, which gives you the structural constants, which are important information. Okay. Okay, so let me just, even though the expressions are complicated, let me just write down some simple formula just to tell you that they do have a nice structure. So there is a way to write the Wilson loop expectation value, which is this Bessel function in terms of the contour integral. So you can write the Bessel function in terms of this contour integral, this is the measure. And then if you apply this relatively complicated procedure, you can, in the end, realize that the correlation functions of any number of these operators can be written as a simple contour integral with an insertion of a product of certain orthogonal polynomials. Okay. So you map the correlation function in this topological subsector to some integrals or product of orthogonal polynomials. And these orthogonal polynomials are built out of these derivatives of Wilson loops. And then the structure constants of the actual operators, which are actually physical information, because as I said before, they are related to the more general physical operators. They are just related to the structure constants of multiplications of these polynomials. So there is a nice mathematical structure which relates these orthogonal polynomials to these operator insertions. Okay, so you can use this and try to match it with strong coupling. It's actually quite non-trivial to do this. It's a fun calculation, but of course I don't have time to go through the details. But once you have this expression, you can just start expanding these polynomials at weak and strong coupling. You find, for example, that these polynomials becomes the usual Chebyshev polynomials at weak coupling. And then you do this integral, and you find here 2 and 3 point functions. And you realize that this precisely matches with the perturbative calculation. So at weak coupling, all you're doing is just you have a product of matrices. Remember that these are adjoint operators inserted inside the Wilson trace. And so you have a trace, product of matrices. And then, so we're doing planar limit here, so you just say one planar contraction of these operators, which gives you this. So in the weak coupling limit, this complicated integral will produce precisely what you expect. Okay? And you can also match subleading. A strong coupling, you can do the same. Now, these polynomials with strong coupling become Hermite polynomials. So in general, there are some orthogonal polynomials that interpolate between Chebyshev and Hermite. And if you do the calculation, in this case, you get again precisely what you expect. Now, in the limit g going to infinity, g is a root lambda here. In the limit g going to infinity, the 2 point and 3 point function have this form. So what is alpha? This is alpha factorial. This is just the number of contractions of free fields in AdS2, products of free fields in AdS2. So this phi to the L will be dual to a composition of fluctuations y that I had before, y to the L. Then the 2 point function will be y to the L, y to the L. Now it's not correlation function of matrices. Everything commute in this strong coupling limit because we just have this bosonic fields in AdS2. And indeed, this correlation function now just gives L factorial. It was giving 1 at weak coupling, and it gives L factorial at strong coupling because we just get now free fields in AdS2. And for 3 point function, you get this, which is the number of weak contractions that you have for free fields. You just count for contractions. Okay? And you can also check the subleading term, and it all matches with AdS2 calculation. So here is some diagrams that you do. So this, for example, for say this would be 5 to the 4th, 5 to the 4th. So what the L factorial will come from the leading term will be from the number of contractions here. And the subleading term will involve also this interaction. And they all match this localization calculation. Okay. This was a little bit quick, but if you're interested in more details on this, you can look at these papers that I wrote with commands, where these are described in detail. Okay, so let me conclude and summarize. So these correlation functions on the Half-BPS Wilson loop, as I tried to explain, they have a structure of a P=1 conformal system. So they are constrained by conformal symmetry in 1 dimensions. At strong couplings, this can be computed by AdS2 Witten diagrams, where the AdS2 is the string Worldsheet, and the Witten diagrams describe the interactions of the string fluctuations. One question is whether there is a manifestation of integrability in these amplitudes. It will be interesting to understand whether there is a notion of integrability for a theory in AdS2, whether Witten diagrams behave nicely as matrices of integrable theories. And there is a quite large topological subsector of this one-dimensional conformal theory, which is captured by localization. And it may be interesting to ask whether there is actually a topological string subsector of the full theory which just captures this topological subsector. Maybe there is some kind of topological version of holography which is embedded inside this system. So, as I commented before, it's plausible that some of the non-protected data in this series, like for example the dimension of this 5-6 insertion we were discussing about, it's possible that it may be fixed exactly by integrability, or maybe perhaps an exact solution of the system will come after we combine all the data from localization, integrability, and maybe bootstrap. And if I just have 2 minutes, let me just flash the last slide. So some other directions that I didn't discuss, just in case you are interested. So there is one direction that I didn't touch at all. I always focused on the fundamental representation of the Wilson loop, but you can discuss higher representations. And for example, there is a story which is very analog to the giant graviton story that David was talking about. In this context of Wilson loops, there are also giant Wilson loops. So if you take traces in large symmetric or anti-symmetric representations, so these are Young tableaus with, say, rows with order of n boxes or columns with order of n boxes. Those are described not by fundamental strings but by D-branes. So you have D3 and D5 branes, which wraps either a 2-sphere inside the AdS5 or a 4-sphere in AdS on the S5. So you have a D3 brane with AdS2 process 2 forward volume, or a D5 brane with AdS2 process forward volume. So these are the D branes which have exactly the same symmetries as the Half-BPS Wilson. They have the SL2 coming from AdS2. They have the SO3 in this case, then they have the SO5. So these are like the giant and dual giant Wilson loops. So it may be interesting to study, for example, the generalization of this Wittenberg calculation that I did in the context of this D-brane. So study D-brane fluctuations, expand the DBI action and the redoff interactions, and then try to match that with some predictions for Wilson loops in higher representations. Okay, another story that I didn't touch at all was the case of the ordinary Wilson loop. So I focused on the case of the Wilson loops with the coupling to scalars. But actually, you can also describe the ordinary one, just into the IA. So what is it that we have to do here? So the proposal that was made long ago again by Fernando Juan and later also Koczyński and Salvi is that what this should correspond to is to letting the fluctuations around the S5 direction have Neumann boundary conditions instead of Dirichlet. So if you pick Dirichlet, it means that you fix those fluctuations to have to behave like this theta I coupling at the boundary. If you take Neumann, you don't fix it. And then it's natural that that should correspond to the operator where you don't have any coupling to the scalar. Okay. So we studied this recently, this paper with Sachin and Zachary, and there's another paper without me. So it's interesting that you can describe this, as was pointed out by Koczyński and Salvi. You can build some kind of RG flow from the ordinary Wilson loop to the supersymmetric one if you consider this more general operator with a coupling constant here in terms of multiplying this by 6. So consider this. You can view this from like defect, one-dimensional defect field theory logic as some kind of relevant deformation of the non-supersymmetric Wilson loop defect. You add this deformation, and so you deform your operator, and then it turns out that this, you can view this as a one-dimensional coupling that runs. It has a beta function, and this is the beta function at with coupling. So you can see that it has 2 fixed points, zeta equals 0 and zeta equals 1. So the 2 fixed points are precisely so zeta equals 0 is the non-supersymmetric Wilson loop, and zeta equals 1 is the supersymmetric Wilson loop. So this operator describes an RG flow in one dimension from the non-supersymmetric ordinary Wilson loop in the UV to the supersymmetric one in the IR. Okay, and you can compute various things, like the dimensions, the of this insertion at weak and strong coupling. So the weak coupling, again, I've not done these calculations long ago. So at this non-supersymmetric point, it was like 1 minus something. This is the one I showed you before, and this is the analog story in the non-supersymmetrical smooth. So now strong coupling, these dimensions go to 0. That's precisely what you expect when you go from Neumann to Dirichlet boundary condition. So the AdS-CFT relation for this massless fluctuation is delta minus 1 equals 0. So you have actually two choices, delta equal 1 and delta equals 0. Delta equals 0 is this, more precisely, means that dimension goes to 0 as strong coupling is 1 and strong. And then you can also compute the Wilson loop expectational value at weak and strong coupling. And what is interesting is that, well, it's natural to view this Wilson loop expectation value as some kind of partition function for the one-dimensional theory, and then the log of that is like a free entity. And you can check that if you take these results that we computed, that this f actually decreases under this RG flow. So this is an example of a one-dimensional version of the F theorem that works for this this defect, one-dimensional defect flow from ordinary to supersymmetric Wilson. Okay, this was quick, but I thought it would be interesting to just flash it a little bit. If you're interested, you can look at that paper with Arkady and Karin. Okay, so let me stop here. Thank you.
So any questions?
Maybe just clarification. If you can state again what is the one-dimensional system actually, the one which does that? Since you refer to it all the time, the 1D system.
1D system is just a system of, defined by these Wilson lines.
But in terms of action,
Well, there is no way.
so that's what I'm.
So it's a system. It's a system of correlation functions. So there is a spectrum of operators. They have their scaling dimensions, and then there's correlation functions. And
These are the observables, and
yes. Yeah.
there is an integral. And it's one-dimensional because it's different time.
Yeah. So there is a way to write this more like an action, but if you write this Wilson loops in terms of, you can write these path order traces in terms of fermions. Right. So introduce world line fermions. Right. But this action is still it still couples to the four-dimensional fields. So in that sense, it's not a purely. Well, if you just focus on the correlation functions on the line, everything is just one dimension. But in principle, you could integrate out the four-dimensional field. Then you get some non-local. It's a non-local one-dimensional conformal. Well, once you write it in terms of fermions, it becomes similar to SYK a little bit, except that it's non-local. So it may be a little similar to a version of SYK that Gross and Rosenhaus wrote down, where they had some local kinetic term and they had exact SL2R symmetry. This looks a little bit like that. There's an exact SL2R symmetry, and it's a non-local one-dimensional system.
So when you start considering D-branes, I guess you can also consider embedding them such a way that you get higher dimensional defects, right? On the CFT side?
Yeah,
You can make a link maybe with what people have been doing recently with codimensional non-defects.
Yes. You can study those as well. So
does that add anything to that discussion? Because now you can do have this calculation in done. I'm not sure. I know the latest. From the bulk side. I mean, because I know at least the papers I know they're working on the case theory side.
Yeah. I don't think much has been done on the bulk side. But yeah, so there you will have this kind of three-dimensional defects, and you will have a three-dimensional conformal symmetry on them. So you have a similar story with you can have insertions on those defects, which describes the deformation of the defects, and they will be covered by three-dimensional conformal symmetry.
But in this case, are you talking about these papers of Marius?
Yeah.
In those cases, also the 1-point functions are different from 0.
Yeah.
Those are what, okay, so the 1-point function that you're talking about are bulk 1-point functions. So you have a bulk operator in the presence of the defect. Those are non-zero even here.
So these are like 2-point functions between the non-local and the local
Exactly.
operator.
Right. Those are non-zero even here. I mean, that's true for any. But I don't think they studied, say, just correlation functions on the defect itself by just studying fluctuations of the corresponding. I guess there will be some kind of AdS description of that. Two-dimensional one.
So AdS 3 or AdS 4 is
Right.
AdS 5, and then you need to integrate over that.
Right.
I guess if it was easy.
I haven't looked at
How's this story also being worked out for the AJM solution?
that. You mean the story of correlation functions?
Yes.
Part of it has, but not this, not the analog of this explicit 4-point function calculations. So, indeed, someone should do it. Just take the signal model on AdS 4 plus CFT II. Do some analog calculation. I mean, the representation theory has been worked out. It's clear what you should expect and what is the spectrum of insertions.
But it's
So
also
there is a little bit
dimensions
less,
model, right?
yeah, there is a little bit less control there on the localization side. Because there is no analog of this larger class of 1/8 BPS operators, which you can use to reconstruct information about the insertions on the BPS model. I mean, there is some natural calculation that one could do. I don't know if you can do as much as can be done in any.
If there are no further questions, let's thank Simone again. The letters you may think past